a few key points about enthalpy changes. The first is that the enthalpy change of a reaction depends on the moles of product obtained. So, for example, this reaction, the reaction of nitrogen gas with 3 moles of hydrogen gas to produce 2 moles of ammonia, has an enthalpy of minus 92.22 kilojoules for that reaction. If instead of if instead of making 2 moles of ammonia, we made 4 moles of ammonia, then we would get double that amount of kilojoules. If we only produce 1 mole of ammonia, we would only get half of that enthalpy change. So the enthalpy change of a reaction is meaningless unless you include the chemical equation which it applies. So it's not only, you not only need to know that the enthalpy change of the formation of ammonia is minus 92.22 kilojoules. You need to put the equation of exactly how the reaction, how the reaction works. What are the coefficients in those reagents and products? Because if you, for example, brought this reaction, so half to obtain only 1 mole of ammonia, then the enthalpy of that reaction as it is would be half of the previous one. So I'm going to ask you to do this exercise because I cannot think that there is a single chemist that can resist to set an exercise of anything in which doesn't require you to use to do some calculations using moles. The reaction of combustion of carbon, so reaction of carbon with oxygen to produce CO2, has that enthalpy change, minus 393.15 kilojoules. It's an exothermic reaction. So what would be the amount of heat release when you burn 1,320 grams of carbon? So what would be the energy release when you start with 1,320 grams of carbon and you have enough oxygen so it all reacts? Stop the video now, please. So hopefully you remember that equations tells us about moles, not about grams, at least not in an easy way. So if I look at the equation, I see that 1 mole of carbon produces 193.15 kilojoules of energy. So if I know how many moles of carbon I've got in the question, then I will know how much energy they are going to produce. So I need to convert my 1,320 grams of carbon into moles of carbons. And I do that by using the formula and using the molecular mass of carbon. The number of moles of carbon will be the mass of carbon, 1,320, divided by the atomic weight, in this case of carbon, which is give or take 12. That is 110 moles. So how much energy will the reaction release if we burn 1,320 grams? Well, minus 393.15 times 110. And that is minus 43,000 and a bit. Again, I need to remember the minus sign because it's an exothermic reaction and that hasn't changed. It's just now because I'm burning more moles of carbon, I get more energy. Enthalpy changes are associated with the state of the reagents. So if you look at these two reactions, they both show something similar. The reaction of hydrogen and oxygen to produce water. In one of them, both the hydrogen and the oxygen are in gas form and the water is also in gas form. But in the second one, the hydrogen and the oxygen are in gas form, but the water produced is liquid. And as you see, the enthalpy is different. So the fact that you're producing water in gas form or liquid form affects the enthalpy of the reaction. And why? Because changes in the state of the matter from solid to liquid or liquid to gas or the other way around involve energy changes. So when you condense water, when water moves from gas to liquid form, that's an exothermic process, and a certain amount of energy is released, and that is this minus 88.02 kilojoules is embedded on this value. So the physical state of the compound must be included in the thermochemical equation. So the proportion of the reagents and the reagents and the products are going to make the coefficients, the proportion of reagents to products, and how many moles of each one or the other you're going to form, and also the state, whether they are solid, liquid, gas form, aqueous solution. Reactions that are endothermic in one way are exothermic in the reverse direction, and that kind of makes sense. So when you have a reaction, you're actually having two pieces of information. One, what happens when the reaction goes from the reagents to the products. For example, in the reaction in the top, our 2 moles of hydrogen gas react with 1 mole of oxygen gas to produce 2 moles of water gas, and that is an exothermic reaction, and it releases minus 483.64 kilojoules. If I go the other way around, if I go the other way, what we call in the reverse direction, if I have water, 2 moles of water gas, and I release 2 moles of hydrogen in gas form and 1 mole of oxygen in gas form, that enthalpy changes sign, because what was an exothermic reaction going forward is now an endothermic reaction going backwards. If a reaction of hydrogen and oxygen release that amount of energy, it stands, when you make water, it stands to reason that when you want to split the water into the hydrogen and the oxygen, then you will need to communicate that energy for the reaction to happen. So the value is the same, the absolute value is the same, and the sign changes depending on if you go in the forward or reverse reaction. This rule applies to all reactions and also to physical changes. So something that is not a chemical reaction, it's a physical change. So for example, if you go to, this is the formula for acetic acid. So if you have acetic acid in liquid form and you transform it into acetic acid in gas form, you vaporize it, you will need to communicate some energy. This is an endothermic reaction, plus 29.1. If you have acetic acid in gas form and you condense it into acetic acid in liquid form, then that reaction will liberate 29.1 kilojoules per mole of acetic acid. So again, the absolute value is the same, but the sign changes depending if you're looking at the forward reaction or the reverse one.